Thank you, Junio, for the nice introduction. And the title of my talk is Intelligence on Silicon from DNN Accelerators to Brain-Mimicking AI-SoC. The intelligence on silicon sounds like a little bit ambiguous and abstract. So before I start my talk, I would like to show you a short video clip. So can you imagine the name of this robot? The name of this robot is Intelligent SOS Robot. It was invented in 2002 at KAIST to encourage more KAIST students to major in the SOS design by providing them the future vision and dreams about the SOC applications. The name of the robot, Intelligent SOS Robot, exactly matched with three topics of my talk: AI, or DNN Accelerators, SOC, the brain-mimicking AI-SoC, and the humanistic intelligence system such as robot. So just three topics, that's all. So let's get started with AI, or DNN Accelerators. The DNN concept was introduced 1970 and almost 1990. Almost all concepts of the CNN and RNN were established. And then many neural networks proposed for the image detection and image recognition and even image generation by GAN. However, the real chip implementation of the CNN is very late, and almost 2008, the first CNN chip, CNN IP is embedded inside complicated SoC and presented at ISSCC. And the real serious and meaningful CNN chips or DNN chips first presented at ISSCC2019, and also other groups like MIT and Catholic University Leuven and Michigan and Tsinghua and Hokkaido University presented many DNN chips. Most of the DNN chips aimed at the cloud-based server. They support very high computing power and huge memory bandwidth for fast and accurate learning as well as inference. Recently, many chips presented for the mobile-based application for the real-time response and specific AI. Their resources, such as computing power and memory, are limited, and low power consumption is very important. Cloud-based AI computing, recently most intelligent operation is performed inside the cloud, and the smart speaker just send data and receive the result, so no smart at all. Intelligent operation is not performed inside the smartphone. Recently, inference engine tried to install inside a mobile and edge device for the high-speed response, a real-time response. But the mobile DNN application, its application scope is very wide, from automotive to IoT, and each application requires different speed and different power consumption. If you calculate the energy efficiency, or the inference speed divided by power consumption, you can find all the DNN applications, mobile DNN applications, require high energy efficiency, more than 1 TOPS per watt. And also, because the application range is so wide, so one chip should support multiple applications. So flexibility and versatility of the chip is very important. Recently, many researchers found reconfigurable hardware architecture is very effective to support high energy efficiency and high flexibility. Even the layer-by-layer optimization with the DRP, dynamically reconfigurable processing, is possible. This graph shows the performance of DNN ASICs. The triangle shows the DNN ASICs with recomputable hardware. And compared to the conventional DNN ASIC with recomputable hardware shows better performance in terms of energy efficiency and throughput. And how can we make it? This is a typical DNN Accelerator architecture. And we can reconfigure the process element, and also we can reconfigure the bit precision of the number system, and also memory bandwidth. Memory bandwidth will be covered later at the processing memory part, processing memory or computation memory part. So for the time being, I would like to focus only on the processor configuration change and bit precision configuration change. I selected 4 typical reconfigurable ASICs. One is UNPU. It has a fine granularity of the bit precision configuration, and processing element configuration in fine granularity too. And another extreme is DNPU. It has coarse bit precision granularity and coarse processing element configuration granularity. And KAIST and Thinker chip also has a fine granularity and coarse granularity, and coarse granularity and fine granularity. Let's think about the P reconfigurability first. Different networks require different operations. Convolutional layers require heavy usage of the max, but less access to the memory to patch the weight values. RNN and the fully connected layer requires more access to the external memory to fetch the weight rather than the processing element operation. So in order to support such a different requirement, KAIST introduced the NPU architecture. It integrated separate convolution core and RNN core to support the both CNN and RNN. Its performance is quite high, and 8.1 TOPS per watt power efficiency can be obtained. However, in this system, if you want to use only the convolution layer, then RNN is in idle state, so that's the waste. So the Tsinghua University professor in group introduced the Thinker architecture. He focused only on the processing element, and each processing element is composed of convolution blocks and a fully connected block, and RNN block, and a pooling block. So you can reconfigure the processing element itself. So you can increase the utility. However, it's not optimal because if you select only the CNN, then the other part of the processing element is in idle states. Later, the KAIST introduced the UNPU architecture. It has unified P array. So each P cannot be divided in sub-parts. So the entire P can be reconfigured into the CNN and RNN. So all processing element will process the RNN, where a part of the processor allocated to the convolution and a part allocated to the RNN, where all the processing element will process the convolution. Okay, bit precision. Each neural network requires different weight precision. For example, RxNet, if weight precision is more than 7 bit, you can achieve the maximum accuracy. And VGG16, if you use more than 10 bit for the weight precision, you can achieve the maximum accuracy. So if you can change the weight precision according to the target neural network, you can optimize the performance. Japanese Hokkaido University Professor Motomura introduced the KAIST architecture. He adopted the bit serial processing element. Because of the bit serial property, you can easily change the precision, just a repetition of the processing element operation from 1 bit to 4 bit continuously. And KAIST also adopted bit serial processor, and but the variation range is wider from 1 bit to 16 bit continuously. So the UNPU has a unified processing element and fully variable weight precision. So each layer, the same chip, can be reconfigurable into the different types of neural network and different weight precision. For example, the first layer is a 16-bit or convolution layer, and layer 3 is a CNN and RNN together and a 4-bit weight precision. So UNPU chip is implemented with 65 nanometer technology, and because it can utilize all the processing element, so area efficiency is quite high, and also power efficiency is more than 50 TOPS per watt. Its chip is assembled and integrated together with a smartphone to recognize human emotion. Local learning. Recently, the mobile and edge device try to integrate not only the inference engine, but also the learning engine to adapt the environmental change and for the personalization. But the learning is quite challenging compared to the inference. Learning is composed of 3 stages. First is feed forward, is exactly the same as inference, and back propagation, and weight update. In order to calculate the weight update, you have to calculate the weight gradient, and weight gradient requires the intermediate data generated during the feed-forward stage. So you need to use size of memory to store all the intermediate data to calculate the weight gradient. And also the 3 stages of learning should be repeated to the entire batch size. So you need a long learning time. For example, ResNet 50 with 1.2 mega images, it takes 11 days for the training. And also, more than 16-bit floating point accuracy is necessary for the exact training. Such heavy computational requirement, only the server at cloud can support. But cloud learning has some problem. In order to receive the AI service, you have to upload all your data, even your private data or your confidential information should be uploaded. So privacy and security cannot be protected. So recently, Google introduced federated learning for the secure local learning. The concept is very simple. Cloud server broadcasts pre-trained neural network to mobile devices. Each mobile device uses the pre-trained neural network and uses its own local learning engine and also local private data, re-educate the shared model. And then after the learning is completed, only the weight from each mobile device is updated uploaded to the cloud server, and the cloud server updates the shared model. In this scenario, you don't need to upload your raw data, so the privacy can be protected. However, how can you support local learning on your mobile device? Mobile device cannot support such high computing capability. This year, KAIST will present paper 7.7 for the mobile DNN learning processor. its power consumption is 367 milliwatt, and its energy efficiency is 4.4 times higher than the GPU. The secret is they use two-number system, 16-bit floating point system and 8-bit floating point system. Among the 16-bit floating point system, many pixels can be converted into the 8-bit pixel. So in the 16-bit pixel floating point image, there are many zeros. So the MAC operation for the 16-bit operation can be reduced more than 90%. So you can save the allowable energy and speed up the operation. Of course, 8-bit floating point image is overhead, but compared to the gain from the 16-bit floating point MAC operation reduction, it's affordable. And the chip is assembled on the robot, and the robot uses that chip to and also its private data to learn and quickly find its destination. And the right-hand side, the graph shows the required energy for the mobile DNN, the LNPU, learning NPU of KAIST, compared to the GPU and AP. Compared to the GPU, 71% of energy reduction can be obtained. And reinforcement learning is regarded as the optimal machine learning algorithm to interact optimally with the environment. The intelligent agent receives the state from the environment and using the complicated mathematical algorithm like a Q-learning and generate action. And then the environment gives the reward as the feedback. But recently, deep reinforcement learning tried to use DNN instead of the complicated mathematical algorithm. So the DNN, using the DNN, you can easily generate the action from the state. And then the action, generated action, and the reward is accumulated until your batch is filled. After the batch is filled, policy update or the DNN learning starts. And after the DNN learning completes, then again, the action generation and action accumulation starts. The KAIST introduced the mobile DRL accelerator as a paper of 7.4 in this ISSCC. And the secret is they reduce memory access by data compression and dynamically adaptive data reuse scheme. So power consumption is less than 200 milliwatt, and the performance is 204 gigaflops. The chip is used for the secured learning in unknown environment for the fast adaptation with on-site data. For example, quick decision-making for autonomous driving, and autonomous robot arm control, and autonomous drone control. Humanistic intelligence is very important for the collaboration between human and machine. Currently, the machine doesn't have any means to recognize the status of the users or the state of the human being. Through the humanistic intelligence technology, the machine can understand the human being or users, so the real communication is possible. Real dialogue, not two monologues, is possible. And also emotion sharing is possible. So the real collaboration between the human being and machine is possible. Because there is a AI phobia because of lack of the humanistic intelligence. So there is no communication, no compassion, no mutual understanding, so no collaboration. So people worried the AI may replace human being. However, if we introduce a humanistic intelligence system, then mutual emotion sharing is possible, and mutual understanding is possible, and real collaboration between robots and human is possible. So human skill is augmented by the AI. Then how the machine can recognize or understand the human state? It's very simple. There are many user signals, verbal, auditory, gestures, and facial expressions. And using the local learning and deep reinforcement learning, machine can understand the emotion and conversational status and verbal content. Not only the recognition, even the understanding is possible. So under what context the users are in, that kinds of user understanding is possible. KAIST developed the DNPU, using DNPU for the gesture recognition and speech recognition, and also using UNPU for the human emotion recognition system. This is an example. DNPU is installed intelligent SoC robot.
Wake up.
And speech recognition is possible.
Follow me. Show me a map of China. Follow me. Bye-bye.
Okay, let's move on to brain mimicking. There are two types of approach in brain mimicking. One is a microscopic brain structure mimicking, like, for example, the neuromorphic approach. In neuromorphic approach, also there are two types. One is synapse-centric, and the other is neuron-centric. Synapse-centric usually implemented with memory. So SRAM-based and non-volatile memory-based like RRAM, PRAM, and MRAM. According to the brain scientist, our brain is made of many functional modules. So each functional module can be modeled as a mathematical formula or software or CPU or even the neural network. And those functional modules can be connected together through the connectome to obtain higher intelligence. That is the functional model approach. Neuromorphic approach try to mimic the neuron behavior. So synapse-centric try to model the synapse, and neuron-centric try to model the action potential of the neuron with the analog circuit. The most famous SRAM-based neuromorphic chip is True North. True North, they use SRAM to store the weight value, and input spike multiplied with weight value, SRAM weight value, and all the input summed up, and then through the nonlinear function, the output spike is generated. So you don't need to fetch the weight value from the external memory, so less power consumption than the von Neumann architecture. However, the SRAM cell is composed of many transistors, so large area is required, and the integration scale is limited. NVM can change the SRAM with simple memory cell, like a register in RRAM. So in RRAM case, you can store even the analog value as a weight. So compact analog SS spike neural network can be realized. But these approaches looks very similar to memory-centric computing. In memory-centric computing, where the computing architecture field, there exists a von Neumann bottleneck. The external DRAM access requires a lot of energy, and also the bandwidth is limited. So the von Neumann bottleneck limits the total computer system. So recently, near memory processing is tried. Near memory processing means processor moves too near to the memory, like a high bandwidth memory, and 3D stack. And also processing in memory, or computation in memory, or in-memory processing, or in-memory computation, whatever, they try to embed the processor inside the memory to reduce the distance, and also share some mathematical operation with the memory and the processor. National Tsinghua University Professor Marvin Chang proposed RRAM NV CIM. CIM means computational in memory, using the RRAM. And he implemented binary input and ternary weight and convolutional neural network, and fully connected network is implemented. And Professor Wu Chang of Tsinghua University proposed the complete operation of the RRAM array for the face recognition. As far as I know, this is the most advanced RRAM-based AI circuit, AI system, and it achieves more than 96% accuracy with the MNIST. And the neuron-centric method, the neuronal behavior is simulated with CMOS neuron with integration and fire model to realize a low energy spike neural network. However, in order to simulate each neuron, many transistors are required, so the integration scale is limited. KAIST try to integrate together the heterogeneous, the many-core processor together with DNN, and human brain has many functional modules, and each module is modeled as a many-core and a deep neural network, and they are connected together as a NOC. NOC plays the role of a connector. And the DNN plays the role of attention, visual attention. So visual attention select only salient object from the input image, and then that part sent to the many-core processor, and many-core processor process only that part for the image recognition to speed up and reduce the power consumption. And not only the bottom-up attention, but also the multi-attention and top-down attention means the knowledge stored inside your brain can be used for attention. And also the spatial temporal attention, the temporal change can be given, the attention can be given to the temporal change. All those mechanisms are converted into the attention engine, and embedded inside a complicated AI SoC and presented at ISSCC as a paper, and also we did a demonstration. Okay, let's go back to the intelligent SoC robot. What is the intelligent SoC robot? Intelligent SoC robot try to integrate AI software and AI SoC together on a brain board, and that brain board is installed inside the robot. And then the robots can compete each other in taekwondo game or the mission game. The game started from 2002, and every year more than 100 teams have participated. And this is the Korean website. And from this year, with Professor Wang Jiwa of the Tsinghua University, I would like to start this competition in mainland China. And this is the mainland China website. And I'll show you the example intelligent SoC robot. So 100% autonomous AI robot. This is a mission game, and it should complete 10 missions within 8 minutes. Through this game, we can provide the future vision and dreams to potential SoC designer. Okay, in summary, I explained mobile DNNs. The energy efficiency is very important, and the reconfigurability is essential. The bit precision and PE configuration can be reconfigured to obtain the high energy efficiency. And brain mimicking AI SoC, there are two approaches, neuromorphic approach and functional connectome approach. And in neuromorphic approach, the Synapse Centric usually use MVM and SRAM. They usually take some PIM architecture, processing in memory architecture. And neuron-centric usually use the analog circuit to mimic the action potential. And functional connectome, I introduced a visual attention model for the functional model. And humanistic intelligence, with the help of the mobile DNN learning and mobile DRL and user understanding, enable the communication and compassion and collaboration between robot and human being. So DNN and AI SoC and humanistic intelligence combined together to open the smart machine, next smart machine world. I would like to conclude my talk with this sentence. I like this sentence by the Marshall McLuhan, Canadian philosopher. He said, "We become what we behold. We shape our tools. Tools for us is a VLSI, SoC, and IC, or CPU, DRAM, whatever. And afterwards, our CPU shape us." I would like to change this. We become what we behold. We shape our dreams, and afterwards, our dreams shape us. Thank you for your attention.